Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder if we could control computers just by thinking about it? And not just any computers, but ones that can adapt to us in real time. Well, this new study explores just that, looking at a super cool way to make brain-computer interfaces, or BCIs, smarter and faster. Imagine you are trying to control a video game with your mind. Most systems wait a set amount of time before guessing what you want to do. But what if your thoughts are clearer sooner, or maybe take a bit longer to form? Waiting too long is annoying, and deciding too early can lead to mistakes. That is the problem this research tackles. They're trying to make BCIs that don't just guess after a fixed time, but can intelligently decide exactly when to make a prediction based on how much brain evidence they've gathered. It is like a smart detective that knows when it has enough clues to solve the case, rather than just waiting for the clock to strike a certain hour. The core idea is something called adaptive temporal decision making, or ATDM. Instead of a rigid timeline, ATDM learns to be flexible. But here is a big hurdle: current methods for reading brain signals, especially using EEG, which is electroencephalography, aren't really built for this flexible timing. They often struggle to give reliable information when the observation time keeps changing. Plus, many existing methods are really specific to one type of brain signal task, like focusing on visual patterns. They don't work well across different brain activities. So, what did these researchers do? They came up with a new system called ProtoTrigger. Think of it as a two-part smart brain signal reader. The first part, called local feature extraction, or LFEE, uses something called prototype learning. This is a fancy way of saying it compares snippets of your brain activity to learn prototypes, or typical patterns. This helps extract really stable local information from the brain signals, no matter how long the observation window is. It's like having a library of common brain words and seeing how your current signals match them. Then there is the second part, global evidence aggregation, or GA. This part uses something like attention, but with a twist. Instead of just looking at what's happening now, it uses evidence prototypes to figure out which parts of the brain activity over time are most important for making a decision. It's like assigning importance scores to different parts of the story based on whether they strongly support the main plot. This helps the system focus on the crucial brain signals and ignore the noise, especially as more data comes in. They tested this ProtoTrigger system on 3 different types of brain signal tasks: steady-state visual evoked potentials, or SSV-EPs, motor imagery, or MI, and a custom dataset they created called RFH-VEP. These are different because they involve different kinds of brain activity. SSV-EPs are about responses to flickering lights. Motor imagery is about imagining movements, and RFH-VEP combines both. This was a good way to see if ProtoTrigger could work broadly. And the results, pretty impressive. In offline tests, ProtoTrigger showed state-of-the-art accuracy, time trade-offs across all 3 brain signal types. This means it was really good at being accurate, while also making decisions quickly. It also showed strong generalizability, meaning it worked well across different types of brain activity, which is a big step forward. To really test this, they also did an online experiment with people. They built a real-time system where subjects used their minds to control things in an augmented reality environment. They compared ProtoTrigger to the older fixed window methods. The online results were also very positive. The ProtoTrigger-based adaptive system was significantly better than the fixed window methods. It achieved comparable or even better accuracy, but with a much shorter decision time. This translates to a better overall experience for the user, making the BCI feel more responsive and intuitive. Think about it like talking to someone who instantly understands you versus someone who pauses way too long before responding. Now, let's dig a bit deeper into what makes ProtoTrigger special. They did an ablation study, which is basically where they test the system piece by piece to see what is doing the heavy lifting. They found that the prototype-based approaches in both the feature extraction and the evidence aggregation parts were crucial. When they removed these prototype elements, the performance dropped significantly. This highlights how important learning these typical patterns, or prototypes, is for making the system work well with flexible timing. They also looked at the quality of the state representations, that is basically the internal summary of the brain activity the system creates. They found that ProtoTrigger's representations were good at staying consistent, even as the observation time changed. They led to stable decisions over time, and they were very discriminative. meaning they clearly told different brain states apart. This balance is key for that smart decision-making process. One interesting finding from the online experiment was about user experience. Participants reported feeling more in control and less frustrated with the adaptive system compared to the longer fixed window approach. This tells us that not only is the technology more efficient, but it can also lead to a more enjoyable and less mentally demanding interaction. Of course, like any research, this study has its limitations. They mentioned that the online validation was on a specific type of AR-SVEP BCI and more testing is needed for other BCI systems. Also, they trained the decision-making part separately from the brain signal reader. Future work could explore training them together for even better performance. So, what's the big takeaway here? ProtoTrigger offers a really promising new way to build brain-computer interfaces. By using these clever prototype learning techniques, it can read brain signals more adaptively, making BCIs faster, more accurate, and more user-friendly across different tasks. It's a significant step towards BCIs that feel more natural and responsive, adapting to our individual brain patterns and timing needs. It really opens the door for more seamless mind-machine interactions in the future. What do you think about this? Could you see yourself using a BCI like this one day? Let me know your thoughts in the comments below, and if you enjoyed this deep dive into the latest brain research, please give this video a thumbs up, subscribe to RUBIN'S Mind Lab for more, and hit that notification bell so you don't miss our next exploration into the fascinating world of the mind. Thanks for watching, and I'll see you in the next one.